objects. Okay, so there's a bright nearby Seyfert galaxy. Not so obvious in this photo, but there is a star-like core blown out, oversaturated on the image. It's right there, in addition to the central bulge. Okay, and then in the 60s we found something else that was even more bizarre. We found little stars, in quotes, that had strong radio emission. That's very bizarre. Stars do not give off radio waves. They had spectral lines, but the lines we couldn't identify. They weren't in places that we could, line up with H alpha or carbon 4 or H and K lines of ionized calcium or any of the common lines. They showed absorption lines, okay, that's like stars, but they also showed emission lines. That's very rare. But they look like stars, so we figured they were stars. If they were stars, they're members of our own galaxy, and therefore they must be moving at velocities less than about 300 kilometers per second, because if they were moving faster than that, they would have already left. That's the escape velocity from our galaxy. So we had a bit of a mental block in the early months after discovering these things, quasi-stellar objects, which quickly became called quasars. Quasars. Cool name. Advertisers took it over, and now you can find stars in washing machines and all kinds of stuff called quasars, which you hope don't behave like quasars, because they're violent. You don't want your car to be doing things like that. Anyway, okay. So how far away are these things? That's going to tell you whether they're really stars or not. We finally broke the mental block and thought, these got absorption lines and emission lines, and I'll bet we know the laws of physics are the same everywhere. We know that these are part of the same kind of thing that we must have nearby. I'll bet we could identify these lines, and they're just red shifted or blue shifted way away from where they should be. So once we broke that mental block and looked fresh at these things, we realized, oh yeah, we can identify these lines. But these lines are actually at redshifts of a large fraction of the speed of light. Not 300 kilometers a second, but 100,000 kilometers a second, or 200,000, or almost 300,000 kilometers a second. And they all showed redshifts. And that was the clue. These are objects that are very far away, and they're participating in the expansion of the universe. So we have to backtrack for a bit, and I'll just briefly introduce this, and then I think I'm going to have to call it quits because we've run out of time. But what we're seeing is that the universe is expanding. This is a plot of the positions of galaxies on a diagram of their distance as seen from their Cepheid variables, and then their velocity as shown by the Doppler effect from the spectral lines. So Hubble found, now this isn't Hubble's data. Hubble's data was much noisier and concentrated only down in the early parts here. But even that does show a little bit of a correlation. And so this is called the Hubble law. And the way you can describe this line is very simple. V equals a constant, call it h after honoring Hubble, and then the distance. The velocity is proportional to distance, and the constant of proportionality is h. And h is the slope of this line. This is the equation of a line, and this is the slope. So farther galaxies are moving away from us faster, and virtually all of them are moving away from us. Only a few nearby galaxies are actually moving towards us. Virtually all galaxies are moving away. The universe is expanding like a giant raisin cake. And the raisins that are farther apart move apart from each other faster because there's more yeast between them. And raisins that are really close move apart from each other very slowly because there's not much yeast between them. That's a very good analogy for how the universe is behaving. So there we go, the distance ladder. then is complete. We now have a new way to measure the distance to galaxies. Solve that equation for d, and there it is. Measure the velocity, that's easy. Take a spectrum, find the spectral lines, measure the Doppler effect, and boom, you got the velocity. We know h. Now that took a lot of time, but now we know what h is. Initially, Hubble's value for h was way off. He thought it was more like 500. It's not. It's about 70. But either way, it is directly a proportion. It's a constant, pretty much, throughout the universe. And that's the expansion rate of the universe. And so if you know h and you know v, then boom, you got the distance to your galaxy. At least a pretty decent approximation. So we apply that to quasars and we find out, my God, these things are billions of light years away. They're not a few hundred light years away like stars in our own galaxy. They're billions of light years away. And suddenly you realize, gee, they're kind of dim, but you know what? At that distance, they're not luminosity dim at all. They're up to 1,000 times the luminosity of an entire galaxy. Okay, but the story gets even more bizarre because then, well, there's a quasar. Look at how much brighter it is than its neighboring galaxies. So these galaxies are actually, well, they're galaxies. They're the cores of galaxies. They're related to Seyfarts. They're like Seyfert galaxies on steroids. And the central bright star that you see in Seyfarts are actually moving. Well, they're actually so brilliant that you can't even see the galaxy that surrounds it. Okay? So there's a galaxy in here, but you can't even see it because the central core is so brilliant you can't even see it. But there's a galaxy, a spiral galaxy or something in here. And the core is so brilliant it outshines the whole thing. But here's the weird thing. Look at the brightness variations. This thing is going up and down in brightness with a time scale of months, if not less. And if you look more closely, then you can see they vary in brightness as little as 1 day. How is that possible? Well, that's only possible if these are giant black holes. Okay? If they vary in 1 day, then they can only be 1 light day across because the maximum speed for any physical transmission of any force is the speed of light. 1 light day. Massive black holes with an accretion disk of infalling matter, heated to millions of degrees, will give off enough light to outshine an entire galaxy, even if it's only the size of the solar system. But the only way to do it is if you have a black hole of the right size. And I don't mean a little black hole, I mean a big one. 100 million solar masses black hole. Then the gravity will cause friction in that disk to be big enough to heat up that gas to millions of degrees, and luminosity goes as temperature to the 4th power, big steep power, so hotter things are a lot brighter, and that's how we can explain what quasars are. The nearest example that's related is M87. It's not a quasar, but it is a central dominant galaxy in the heart of a rich cluster called the Virgo cluster of galaxies. And that is the merger product of many galaxies that include the gas, and there's enough gas falling in and stars falling into the center of that galaxy to power a central ball that is bright enough to at least give a hint of being like a quasar. So there's M87, and deep down in the center here is a brilliant star-like core. They're the cores of galaxies. That is what a so-called active galaxy is. Active meaning it's giving off X-rays, it's giving off radio waves, it's giving off all kinds of light that is not typical of stars, because it's not stars. It's the hot accretion disk around a giant black hole. And the orientation of that is such that the beams, well, electrons spiraling into the black hole here will get channeled outwards before they fall in through the event horizon by the magnetic field that is generated by that strong rotation of ionized gas. It makes a solenoid field, and it makes a strong magnetic field, and the magnetic field twists around kind of like a Chinese finger trap, and that channels the very lightweight electrons to be shot outwards. And when it runs into intergalactic gas clumps like this, then it lights them up. And so that's the beams that we see coming out of the black holes in the centers of galaxies. And when those beams slow down by running into stuff and then just sort of start ambling around, that is electrons, charged particles, going through accelerated motion, and that's going to give off radio. Where the radio comes from. Electrons shot out from the cores of these central black holes, slowing down, giving off radio waves as they do so. Radio beams, radio lobes. Same thing. It all comes from the central accretion disk that's only a light day across in the very core. Okay? Chinese finger trap. Okay, that's going to be on my last slide. So I'll recap some of this later when I see you again. We should have quiz number 4. We're ready for quiz number 4 next week. No quiz today. I will have PowerPoint in the form of a YouTube lecture of this whole thing put together, but this is also being taped right now, so you can review what I said. It's probably actually a pretty good thing. It'd be cool if I could turn this into a YouTube, actually. I will see if I can do that. That would save me a lot of effort. Okay, so I'm going to say goodbye to you guys now. It is now 10:50. Class is officially over. Thank you all. I will see you next week. Signing off for now.